In this lab, I modeled the energies and path of a cliff jumper as a point mass. The major fundamental principle I observed was the work energy principle, which basically states that the net work done by all forces equals the change in kinetic energy of an object. I am assuming that the only forces acting in this system are drag and gravity. Thus, the work done by the net force in each time step should equal the change in kinetic energy of the point mass. Even though the cliff jumper is performing a flip into the lake, I am measuring only translational kinetic energy, not rotational kinetic energy. This is because a point mass particle does not have rotational kinetic energy. I found that my model verified the work energy principle mostly, but there was some noticeable variance in the first 0.8 seconds. In order to test the work energy principle, I created a model to plot the changes in kinetic energy in the work done during each time step. Each time step was 0.033 seconds, which equals 30 frames per second that I used when observing this data. The work energy principle is valid because kinetic energy is derived by manipulating the equation for work. By substituting dp dt for the net force and v times dt for dx, you can get the equation for kinetic energy, which is the integral of velocity with respect to momentum, and equals 1/2 mass times velocity squared. Work done equals the integral of force with respect to distance. To calculate the work done by the drag force, I multiplied the drag force, which is some constant b times velocity squared, during the time step by the distance traveled. Because drag force acts in the direction of velocity and the cliff jumper is moving in 2 dimensions, the distance traveled equals the magnitude of the displacement vector. To calculate the work done by gravity, I multiplied the gravitational force, mass multiplied by the gravitational constant of Earth, during the time step by the change in y position, because gravity only acts in the y direction. The program itself works by looping over small time steps. Using simple kinematics equations, v equals vi plus at and x equals xi plus vt, and finding the net force, I am able to show the path of the cliff jumper as modeled and plot the changes in energy and work. Even though the values theoretically vary throughout each time step, because the time steps are so small, I am able to approximate a constant value for the span of the time step. I found the coefficient b, 28.5, for the drag force by testing values and determining which one makes the point mass in the particle in the y direction displace as far as I observed the cliff jumper. I noticed that the x position changed linearly, which means that the x velocity was constant. To find this value, 1.11 meters per second, I found the change between the initial and final x positions over the change in time. To find the initial y velocity, 2 meters per second, I tested different values to see which one matched the peak of the observed jumper. I found the initial position vector by looking at the initial values observed. 0.146, 0.2560 meters. Because I was not given the weight of the cliff jumper or the diameter of the inner tube, I resorted to the internet to find approximate values. I used the average weight of an adult male, 70 kilograms, and the standard size of an inner tube's diameter, 0.9144 meters. I found it curious that the x velocity seemed so linear because the drag force should act in the direction of velocity, which includes the x direction. For most of the video, the cliff jumper is horizontal, meaning that the cross-sectional area, a value that would be factored into a non-simplified equation for drag force in the x direction, is minimal. B, the drag coefficient, was calculated by myself to fit the y displacement of the ball, not the x direction. So it makes sense that the drag coefficient would not be appropriate for the x direction. Ultimately, the model did a solid job of verifying the work energy principle after the first 0.8 seconds. During the first 0.8 seconds, the cliff jumper makes 75% of his total rotation. So this error can be attributed to the work done by the varying coefficients of drags and cross-sectional area that I was not able to take into account. I was surprised that the model seemed to predict a terminal velocity, which you can tell because the change in kinetic energy reaches 0 after 1.8 seconds. The cliff jumper does not have much time to reach terminal velocity. I think part of this can be contributed to the jumper maximizing his cross-sectional area in the y direction by being completely horizontal. However, the observed cliff jumper does not actually seem to approach terminal velocity. I think this variance, again, has to do with the simplified coefficient of drag. If I wanted to calculate the rotational kinetic energy, I could do so by finding the work done by the real system minus the work done in the point particle system. Ultimately, the model could be improved by changing the drag coefficient to vary with time so that it fit the data better.